Hi everyone. I'm going today to present software architecture and green software. First, I am Mu'min Abu Ghazala, working with Professor Henry Muccini in topic software architecture and data architecture. I have more than 13 years of experience in software development and software testing. For a sustainable software architecture, our objective is to offer a comprehensive analysis of software architecture that can be applied in business and academic environments. We analyzed various strategies that can help identify opportunities for optimization and eco-friendly practice, ensuring that we can achieve optimal performance and sustainability. To achieve that, we work on three strategies. First one, energy consumption based on architecture design decision. Second one is energy consumption based on the architecture design of human behavior. Currently, we are working on architecture decision and their impact on power consumption in edge for cloud continuum. First, let's start with energy consumption based on architecture design decision. Actually, the software system is influenced by how it's designed, implemented, and deployed. Certain architecture design decision can lead to more or less efficient use of computational resources, affecting the system energy footprint. For example, designing systems that allow for the intelligent use of a sleeping mode or low power state during period of inactivity can contribute to energy saving. We developed the CAPS, an architecture-driven modeling tool for developing situational aware of cyber physical system. CAPS focus on three views: software, hardware, and physical space. CAPS is built on the conceptual foundation of IEEE 42010. It is an international standard for system and software engineering architecture description. To analyze the architecture, we use the model to code transformation, which take model from the CAPS frameworks, then transform it to a runnable CAP-Carbon simulation project. The CAP-Carbon is Internet of Things simulator, allow you to design, visualize, analyze the behavior of these network in virtual environment. So for decision we need to make actually which solution is more energy efficient, which architectural decision, which architecture decision may limit the amount of data created, transferred, and analyzed. For that, we applied our approach on the UNIVAC Street Science at the European Research Night (NDR) event organized by the University of L'Aquila. We first modeled the case using CAPS, which contain 5 components that mainly focus on monitoring of people count and oxygen level in NDR room. Then we converted the model to CAP-Carbon project to run and evaluate. To improve energy consumption, we decided to change the frequency of sensors. For that, we applied 3 different behavior for NDR case study. These behavior are first sensor run with normal mode only, sensor that run also in critical mode only, and sensor runs in normal and critical mode. As a result of running the simulation, it's important to consider, as we said, the normal as an option to trade off safety, energy efficiency, and data traffic concern. In normal mode, less data, as we see, less data traffic is generated, resulting in high energy efficiency. However, it is also important to note the safety concerns are less addressed in normal mode than critical mode. For that, using normal mode in conjunction with critical mode provide better compromise that address all the concern. Using our framework, we can get the early evaluation for energy and data traffic saving while developing situational aware cyber physical system. This vision of testing the architecture early will improve the process of architecting such a system. For the second strategy, energy consumption based on human behavior, it is actually referred to the amount of energy a social technical system uses, which means creating a system that considers human behavior and uses minimal energy while providing a high quality service. The work actually is in the context of understanding the human social and mobility behavior within an environment monitored by interacting system, and afterward engineering and adopting the system based on those behavior. We consider human equality of experience that could be comfort, could be urban security, and so on as an important factor in our software system design. As you see in the figure, we design a simulation environment that can model realistic human and system behavior. The simulation could help understanding and implementing necessarily changes to improve the quality of real system. Our approach involves 4 layers. The first layer deals with the modeling and simulation of different agents using the agent-based modeling and agent-based social simulation approach. The agent-based model of Internet of Things system consists of 3 classes of agents. The first is, of course, human agent. The second is cyber element, then physical element, then IoT resources, which are all parts of the environment. So here we model not only the human behavior, but also the Internet of Things system within the agent-based modeling. We assign realistic value regarding age, gender, vision, social attachment, grouping, and so on, and run the simulation to input the IoT modeling phases. Architectural model and configuration based on the data received from the agent IoT composition, and the final step process the IoT simulation result by considering the quality of service and quality of experience goals. We applied our approach to crowd monitoring of Uffizi Gallery in Florence in Italy. We gathered data for 2 years approximately regarding human behavior interaction, and then feed our simulation, BidSim simulation. With that, we considered 2 scenarios as you see in the table. One is regarding the usual human behavior that may create congestion, and the next scenario was regarding human grouping and social attachment. We created, as you see in the picture, complex model of human behavior that you can see here, and provided suggestion for crowd management and actual queue management and different service that they are dealing with in Uffizi. We also provided data necessarily for architecture modeling that we are presenting here. As you see in this step, we modeled the IT architecture of a Uffizi case using CAB modeling framework and simulated those models with CAB carbon simulation. The CAB carbon simulation actually considered 6 different architecture model, as you see in the first table, along with the 3 configuration. And so the simulators were also according to the 2 agent based model that I explained in the last slide. As I said in the first table, you can see the various model which vary based on sensor type, on number of sensors, and the second table show the configuration in normal and critical modes that of course impact the data transmission frequency. Here I show the result, and here we define the scenario, specific quality of service and quality of experience goal, and assign a trade-off matrix for decision-making purposes consumed by the system for every 15 minutes as the parameter for measuring quality of service, and then the total count of human gathered by the server every 15 minutes as the parameter for measuring quality of experience. In the table you see energy average, that's the average energy consumed, and the human average, that's the average human capture by the sensor. TS is also the trade-off. The result show in the first item-based scenario that we modeled. Model 3 with configuration 1 provide the highest trade-off score by giving the more preference to quality of experience within the compromising too much of the quality of experience. The second scenario says that model 6 with configuration 2 offers the highest trade-off scores value. So it is different from scenario 1. And so this kind of approach could support design the human-oriented architecture consideration, both human and system behavior in the optimal design decision. We conclude our decision with the fact that our approach could specifically design alternatives by considering quality of experience and quality of service toward a system that provide human and system sustainability. Overall, the result of implementing the proposed methodology would be the development of social technical IoT systems that are environmentally friendly, economically viable, and sustainable in the long term. Currently we are working on architectural decision and their impact on power consumption in edge fog cloud continuum. We are checking the location of a processing for the 3-edge fog cloud architecture with different scenarios and how much impact the power consumption. The goal is to select best architecture that have less power consumption and less data traffic in terms of a processing location. And thanks.